Hello and welcome to Mr. Linford's Math 097 course. This is a talk on section 6.1 and section 6.3 of the text. The topics of today's discussion is going to be about the definition of a radical. In particular, we're going to be talking about the definition of square roots, and then we're going to actually go and simplify some different radical expressions. We're going to be simplifying some square root expressions together, both number and variable. But first, let's remind ourselves what it means for something to be a square root. Now this right here, this is my official definition for a square root. B is a square root of A if you can take that number B, you can square it and get A back. A more common notation is B equals square root A. So this is a very common thing to see, and we're going to really work with this formal definition because this is the definition you're going to see in a lot of math textbooks. So the components of a square root, the square root of 4. Well, I'm sure a lot of you probably would say already, well, the square root of 4 is 2. But remember that what our definition says. We need to be able to take that number, square it, and get 4. Well, okay, 2 squared, that's 4. There we go. That's why it's a square root. But don't forget, there's also a negative root. So let's take negative 2, square it, and we also get 4. So this is where the definition becomes super important to us, and that's why I'm going to tweak around this symbol up here to say plus or minus. When you take the square root of something, there are going to be two solutions, a plus and minus, a positive and a negative. Now, a couple things to think about when we have this definition, and it makes it really easy when we see this b squared equals a definition. Could a ever be a negative number? Is that possible for a to be a negative number? Well, pause the video for a second and try and reason to yourself. Could I ever take a number like b, square it, and get a number a, which is negative? All right, hopefully you took some time to pause the video and think about this. But one of the things we're going to say is, can a ever be negative? Not in the real numbers. So right now, if you're thinking of any number on the number line, there is no way you can take any number on the number line, square it, and get a negative number, because anything squared is positive. Because positive times positive is positive, negative times negative is positive, so there's no way a can ever be a negative number in the real number system. However, I will say this, in Math 169 and in future courses, you will learn about complex numbers, and it turns out in the complex number system we can have a negative a. We can take the square root of a negative number, but that's something for later on. Right now in the real number system, not possible. And like we said, how many solutions do square roots have? 2. A positive and a negative. All right, now that we got this basic idea down, let's talk about other types of roots. We can take all different types of roots. Really, we can take nth roots. We're going to use the variable n to just say any root you want to take. You want to take the third root, the fourth root, the fifth root, the 100th root, whatever. It's all possible. And what you're going to say here is b is equal to the nth root of a. See how I put that little n up there? We're going to talk about this in just a minute. But really, the idea here is that you can take whatever roots you want, because we can apply whatever exponents we want. Radicals are really the undoing of exponents. You can think of it that way almost. Now, when we deal with these radical symbols and notations, there's a couple things to keep in mind. Okay, first up, when we are working with this, we got a couple symbols. We have this big symbol right here. This is called the radical sign. Oh, that is a terrible handwriting. I'm getting a little better with the stylus. This is a radical sign. This n right here, where we're going to put numbers in, this is called the index. We're going to be putting numbers in here in just a minute. And then what's underneath the radical sign, the thing we're taking the root of, whether it's a square root, the cube root, the fifth root, whatever we're trying to take the root of, this is called the radicand. The radicand. So we have the radical sign, we have the index, and we have the radicand. These are all the symbols, and we're going to be referring to them in this discussion and in future discussions in this way. Now, some things to keep in mind. There are these things called perfect indices. Now, a perfect index is where I'm really finding perfect squares, perfect cubes, perfect fourths. Really, anytime I take a root and I get a whole number back. So let's go ahead and buzz through this really quick. 1 squared is 1. 2 squared is 4. 3 squared is 9. 9. 4 squared is 16. 5 squared is 25. All of these numbers right here, all of these numbers are the perfect squares. All of these numbers right here are the perfect squares. And then these numbers right here are my radicands. So perfect index or perfect square means you take some radicand and you take the square root of it, you're going to get a whole number. That's what it means to be perfect. Same thing when we work over here with the perfect cubes. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed, I think that's 64. And 5 cubed is, I believe, 125. That's a 6 right there. Oh, gosh. So the idea, again, is if I were to take the cube root of these radicands, if I was to say to myself, what times itself 3 times gets me 125? Well, I could say 5. That's why I have these perfect cubes right here. These are the perfect cubes. That means when I take these radicands, and I take the cube root of them, I'm going to get a whole number answer. That's the nicest, easiest ones to work with. However, come on, let's be realistic here. We're not always going to have nice, easy answers. And in fact, we typically don't. So what we want to do is we want to be able to work with things like the square root of 32. If you type this in your calculator, you're going to get a long decimal. And in fact, we discussed previously, you're going to get a decimal that goes on forever and ever and ever and never repeats a pattern. That's why all of these radicals that aren't perfect squares or perfect cubes, all of these radicals are actually irrational numbers. The square root of 32, it's like pi. It goes on forever and ever and ever, and it doesn't repeat a pattern. And then we're also going to look at some examples that deal with variables, and we're going to see how we can use those. Now, before we begin, there's a property that we're going to have to use. This is the multiplication property of radicals. This property says that if you take any nth root, if you're taking the nth root of something, and your radicand can be written as 2 things multiplied together, what we can do is we can split up the radical. And we can take the radicals of each thing individually. I don't need to multiply first and then take the radical. I can take the radicals of each one and then multiply it together. That's the big idea here. That's what we want to happen. And this is going to help us actually going about simplifying. Now in this class, we're not dealing with nth roots. We are only dealing with square roots. So for us, we're only going to be working at applying this property to square roots. So we're going to be taking the square root of each of the products, or I should say each of the factors individually. Now, does this property appear familiar to you? Because it should. Actually, this property is really from exponents. This is from our work with exponents. This is the power of a product rule. This is the power of a product rule. That's where we said if you have something like 2x and you're squaring the whole thing, we could apply it to each one and get 4x squared. This is the exact same rule, except in reverse for radicals. Now let's go ahead and actually start applying this. There are a couple techniques I'm going to show you. I'm going to show you 2 main techniques that people were discovering in class for going ahead and simplifying radicals. One is a little more lengthy than the other, but typically it makes work much easier, especially when you're working with really large numbers. So let's take the square root of 32. I'm going to show the first technique that's very common way to show. The square root of 32, I am going to use the property, the multiplication property of radicals. And what we're going to do is I'm going to break up 32 into two numbers multiplied together. Well, what two numbers should I pick? 32, there are a lot of numbers that multiply together to give me 32. There's 1 in 32, there's 2 in 16, there is 4 in 8, right? There's a lot of different numbers and combinations I could have here. So which of these should I pick? Well, I'm going to pick the one that deals with the perfect square. Look at that. I'm going to pick the biggest perfect square that goes into 32. That's 16. Which of these numbers, 1, 2, 4, 8, 6, and 32, which of these have perfect squares? Well, 4 and 16 do, but which of them is biggest? 16. That's the one that's the largest perfect square. That's the one I'm going to take. So I'm going to say 32, I'm going to write that as the product of 16 times 2. Okay? Nothing different from here or here. Nothing different. It's the same expression. Now what we're going to do is let's apply the property, and I'm going to say let's take the square root of 16 and the square root of 2 separately. Well, hey, what do you know? The square root of 16, that's plus or minus 4. And then root 2, well, I can't really simplify that. And there we go. This right here, this is my answer. That's what I want. I took the square root of 32 and I broke it down as much as possible to simplify it. Now, my answer isn't totally simplified as you would think. I'm still going to have a radical in there. That's true, because the square root of 32 is not a perfect square. It's not going to give me a whole number answer. But this plus or minus 4 root 2 is better than the square root of 32. I'll explain why in just a minute, but let's take a look at what would happen if I didn't pick 16 and 2. What if instead I said, let me take 4 and 8. Let me break these numbers down for us. So the square root of 32, let's say that's 4 times 8. Okay, well, I'm going to break up into 4 and then 8. And what do you know? I get plus or minus 2 times the square root of 8. That's not the same answer. Well, actually, it kind of is. Because look at 8. Can't I write 8 as the square root of 4 times the square root of 2? I could keep breaking this down. And the square root of 4 is 2. So I end up with 4 root 2. I end up with the same exact thing. Now, we just need to realize that once you pick something that's a perfect square, once you pick one of those factors, when you are done simplifying that one, you have to check what you have left with. You have to check what you were left with, because it might still need to be simplified. You have to ask yourself, is there a factor of this number that is also a perfect square? Well, 2, no, that's way too small. The only factors are 1 and 2. None of those are perfect squares. Well, what about 8? Well, actually, yeah, 4 goes into 8, and that's a perfect square, so I can keep breaking it down. Now, this is a technique that is very commonly taught, but the problem is that it's kind of difficult to use, mostly when it comes to really big numbers. Oh gosh, what the heck? So, apparently my eraser actually doesn't want to erase. Now, what we're going to need to do right now is come up with a different method. We're going to come up with a different method that's actually pretty easy to apply. It's going to be a little weirder, but stick with me. I'm actually going to do this in green. Let's take 32. And we're going to use the same idea. We're going to break 32 down, but we're going to break it down even further. There's something called the fundamental theorem of arithmetic, and it says that any number, any positive integer, is either a prime number or it can be written as the product of primes, a bunch of primes multiplied together. So 32, that's not a prime number. I mean, look right here. We have all these factors for it. So it's not a prime number. So what this means is I can break 32 down into all of its prime factors. You've probably seen this before from elementary school. Remember factor trees? That's what we're going to do right now. I'm going to break 32 down into two factors. Let's say 16 and 2. 16 I can break down into 4 and 4. And each of these 4s I can break down into 2s. And there we go. This is my what's called prime factorization of 32. I have broken 32 down into all of the prime numbers that go into it. What do I have here? 2 to the 5th. That means 2 to the 5th is 32. I am going to write the square root of 32 as 2 times 2 times 2 times 2 times 2. This is the same thing. Put in your calculator. 2 times 2 times 2 times 2 times 2. That's 32. Now what we're going to do, and this is why I love this method, just because it's almost, once you get really good at it, or once you practice it just a little bit, it almost becomes like second nature. We're going to break this up, and I'm going to make pairs of 2 here. 2 times 2. 2 times 2. And I'm left with one of these 2's. That's okay. I'm just left with one of them. That's fine. Now let's go a little further. I have the square root of 2 times 2. What the heck's the square root of 2? Well, that's the square root of 4. That's the square root of 4 and the square root of 2. And hey, what do you know? I can break these down, and I get plus or minus 4 root 2. I get the same exact thing here. This is a really cool method. What we're doing is we are kind of taking all the primes and we're grouping them together and forcing, in a sense, we're forcing it to have perfect squares. It's going to have perfect squares anyway, just like we saw before, but we're kind of grouping them up together and making the best combinations possible. So these are 2 different methods. I'm going to use both, but I like this method a bit better. Like I said, it works really well with large numbers. Rather than spending all your time typing perfect squares in the calculator and trying to break it down, it's much quicker to just start dividing and getting the prime factorization. It really doesn't take that long, almost like 30 seconds if that. So some steps for this, some steps that we're using. What we want to do, like I said, is, and I'm going to go with I'm going to give this method's steps first. Break the radical, or I'm sorry, the radicand. Remember, that's the thing inside the radical sign. Break the radicand into prime numbers. Break the radicand into prime numbers. The next step that we're going to do, once we do that, make, that's terrible, sorry about that, make groups of 2. Now the reason we're making groups of 2 here is because we're taking square roots. If I wanted to make groups of 3, what do you think we would do? Well, hopefully he took a second to think about it, but if I wanted to make groups of 3, we would make, or if I wanted to take cube roots, we'd make groups of 3. Sorry, I'm kind of stumbling over my words. And if I wanted to take the 4th root, I would make groups of 4. If I wanted to take the 5th root, I make groups of 5. The whole reason is because this is the definition of a square root. What times itself gets me this number? Well, that's what we're trying to do. So for square roots in this class, we're only going to be making groups of 2. And then the last step will be to simplify. That's it. That's all we have to do. It might seem a little lengthy, this method, but really, it's not that bad. And once you, like I said, once you get a little practice with it, it almost becomes routine. You know, it's almost like you're not really doing anything, any too much mental capacity. So let's apply this method and let's see if we can use it for the square root of 8. So I'm going to do some side work here. 8 can be broken down into 2 and 4, and 4 can be broken down into 2 and 2. Here is what's called my prime factorization of 8. So the square root of 8 is 2 times 2 times 2. Well, let's make a pair here. We've got a group of 2. And then I have this 1 by itself. That's okay. We expect that to happen. You're not going to be able to simplify these completely. That's because these aren't perfect squares. So you kind of have to expect that one part here will stay. One part will stay as a radical. The square root of 2 times 2, well, I can kind of skip a step. I already know that's going to be 2. So here's my answer. And in reality, we should be writing plus or minus 2 root 2 to be really technical, just to know that, yep, there are 2 answers to this. Positive 2 times the square root of 2 and negative 2 times the square root of 2. So see, this method isn't that bad. Now let's try 48. 48, we can break that down into 2 and, is it 24? And 24 I can break down into 2 and 12. 12 can be 3 and 4 is 2 and 2. So let's see what we have here. And I'm going to kind of order them so that all the like numbers are together. 2 times 2 times 2 times 2 times 3. That should get me 48. And then let's make our groups. I got a pair of 2 and another pair of 2, and that's standalone 3. So that's the square root of 2 times 2. That's the square root of 2 times 2. Square root of 3. This is a 2. That's a 2. And root 3 is by itself. So my final answer should be plus or minus 4 root 3. There we go. Not that bad. And in fact, just for sake of practice, why don't I use the other method, the one that is most commonly taught for this one, because 50, that's a pretty easy one. Let's break up 50 into two numbers that multiply together, where one of them or both of them are perfect squares. Can you think about the factors of 50 and tell me which factor is a perfect square? Well, a pretty obvious one is 25. So I'm going to say 50 is the same thing as 2 times 25. Well, let's take the square root of 2 and the square root of 25. Hey, what do you know? The square root of 25 is plus or minus 5, and then I have that root 2, which is left, that I can't simplify. There's my answer. So it's as simple as that. Pick which method you like. I will be mostly using this method, especially for really large numbers. But if it's a number like 50 here, which is pretty obvious and pretty straightforward, I'll go with that. Now let's talk about what happens when we have a variable. When we have a variable to deal with. Now this is the reason I teach the prime factorization method. When working with this variable, it's actually just the same method as the prime factorization. Instead of saying x to the 5th, let's go ahead and actually write this in expanded form. And what do you know? I can make some groups here. I have the square root of x times x. I have the square root of x times x. And I have the square root of x. Okay, this is all the same. X times x times x times x times x is x to the 5th. And I just broke it up like the property said I could. Well, this is the square root of x squared. That's the square root of x squared. That's the square root of x. And what do you know? What's the square root of x squared? That's just x. And the square root of x squared is, again, just an x. And then I have a square root of x that can't simplify. That's fine. I kind of expect that to happen. And I end up with x times the square root of x. Well, let's just simplify that a little bit. That's x squared root x. There is my final answer. You could put in a plus or minus if you wanted to. But this idea right here, this is an important idea. The same property applies when simplifying variables as we do with numbers. The only difference is, instead of prime factoring, we are writing in expanded form. And then we make groups of 2. No, I'm running out of space here. Make groups of 2, and then simplify. Easy as that. Let's try and apply it now when we have two things together. What happens when I have the square root of 18x cubed? Well, we're just going to use our property. I'm going to say, well, that's the same thing as the square root of 18 and the square root of x cubed. Okay, well, the square root of 18, let me do this to the side really quick. That's 2 and 9, and that's 3 and 3. So I have 3 times 3 times 2. And x cubed, I'm going to write as x times x times x. I have a pair right here, so that's the square root of, I meant to write 3 squared, and it looks like 32. So I'll just say square root of 9, because I got a pair of 3's right here. Square root of 2's by itself, can't do anything with. I have a pair of x's right here, so that's the square root of x squared. And then there's that x all by itself. So let's try to simplify this. Let's see what we get. My final answer should be, the square root of 9 is 3. Square root of 9 is 3. The square root of x squared is x. And I'm just left with the root 2 and the root x. But you know what? I don't like writing two radicals. We can actually, just like our property said, when we can separate radicals, we can actually put them back together. So we're going to actually put this whole radical of the 2x together. So there's my final answer. I simplified this to get 3 and this to get x. And then we just pieced back together the root 2 and the root x. We are totally allowed to do that. Now, you're going to also see some examples like this one, where I have what's called a rational expression. It looks almost like a fraction. What I recommend students do is try to simplify the radical individually. So simplify it on its own, square root of 300. I'm going to use the other technique for this one. I'm going to use the one where I just pick out what a perfect radicand is, because I can just split this up really quickly into the square root of 100 and the square root of 3. The square root of 100 is just 10, and then root 3 is by itself. So here's what I'm going to do. I'm going to sub this in. Instead of saying the square root of 2 times the square, instead of saying 2, I'm talking about too much math right now. Instead of saying 2 times the square root of 300, we're going to say 2 times what the square root of 300 equals, 10 root 3, all over 30. We're just subbing this in. So this becomes 20 root 3 over 30, which, hey, you know what? I can simplify that. So that means my answer is going to be 2/3 times root 3. That'll be my final answer. So really, I mean, all we're doing here, think of this almost like parentheses. Really, radicals operate as grouping symbols, just like parentheses do, just like absolute values do, in brackets and all of that. Radicals, they work as grouping symbols too. So we're going to use this idea when looking at this problem. A lot of students say, hey, let's go ahead and take the square root of 11, the square root of q to the 11th over the square root of q to the 5th. Well, that doesn't always work out. It will if you take your time with it. But there's another method that's kind of easier. And it relates to what I just said a minute ago. Remember that square roots are grouping symbols. So think back to order of operations. Do you want to take the square root first? Or maybe we can simplify inside first. Just like we try to simplify inside parentheses first, let's try to simplify in here first. Q to the 11 over q to the 5th, that's just q to the 6th power. What do you know? This made my work much, much easier. Now I can go ahead and say that's q times q times q times q times q times q. And I can make some groups. This starts to get a little tedious after a while. So we end up with q times q times q, which is just q to the 3rd power, or q cubed. Now, there's something to keep in mind here, and I'm going to tell you a little shortcut. If I were to take q to the 6th, you can automatically say your answer is going to be q to the 3rd. All you need to do is divide the exponent by 2. This only works with square roots. This only is working with square roots. But you can say that because you're really trying to say, I have 6 things and I'm making groups of 2. How many groups of 2 are there? Well, there are 3. So that's why you can take your exponent on the inside of the radical and divide it by 2. And there you go. This will work. Now, it really works best for even exponents, but we can talk a little bit more later on about what to do when it becomes an odd exponent. But this is a shortcut I think most people like, just because this isn't bad, but it gets a little tedious after a little while, so this kind of helps shorten up our work. So I'm going to actually jump ahead and do problem number 2 here. And I'm going to show what happens when I try to apply this rule. So I have the square root of 125. I have the square root of p, oh gosh, I promise I'll practice more on my stylus, p to the 3rd, and I have the square root of q squared. All right, 125 is really 5 times 25. So I know a perfect square that goes into that right away. And then I have p cubed. Well, I'm going to break that up into p squared and p. And then q squared I'm going to break up. Oh, I'm just going to leave that for right now as q squared. All right, what are my perfect squares here? Well, 25 can break down into 5. P squared, the square root of that is just p. And the square root of q squared is q. And I'm left with my radical 5 and my radical p. So my final answer should be 5 times p times q times the square root of, oh gosh, that looks terrible, times the square root of 5p. So I'm going to group those back together in the end. So I'm kind of applying my idea here. If I'm taking p squared and I divide it by 2, I get p to the first. And if I take q squared divided by 2, I get q. This is a very common idea, and I want you to use this as we go through our problems here. Start using this because it'll help shorten up your work a little bit. If not, that's okay. You can stick with just doing the long method. That's fine. Another problem that we can do, like we said before, when we have a big radicand here, it's probably easier to try to simplify it. So let's take the square root of, okay, 4 over 100 is 1 over 25. H to the first over h to the fifth. Well, that's just h to the fourth in the denominator. I'm using my exponent rules. And hey, what do you know? Let's take the square root of the top and the square root of the bottom. I got some perfect squares in there. Square root of 1 is just 1. Square root of 25 is 5. And the square root of h to the fourth, well, let's see, 4 divided by 2 is h squared. Simple as that, okay? These are the basic ideas for it. I hope they make sense. And if you have any questions, feel free to let me know. We're going to be doing some practice with this set of notes, so give it a try. These two techniques, it's good to know both of them. Have a method that you like best. If you're crunched for time, break down into the prime factors. But if you're like, hey, I got something that's pretty obvious what perfect square goes into that, then just use the perfect square method. Until next time, this is Mr. Linford. If you have any questions, feel free to contact me at Linford, that's KLINFORD at wccnet.edu. That looks terrible, but it's Linford, like the car company, at wccnet.edu. Until next time, take care, and I will see you later.